What's up everybody, and welcome back to another video on SAT Math from the Scalar Learning channel. And this video is part 2 of a 4-part series all about the critical concepts in mathematics tested on the SAT. These categories are derived from the big categories from Khan Academy, and today we're covering Passport to Advanced Mathematics. The first thing that we're going to talk about in this section is quadratic functions. So quadratic functions are a huge part of this section, and we want to start by understanding what does a graph of a quadratic function look like. So it has this very interesting shape, right? It looks like a U, and it can either go up or kind of go down, right? So the first one is kind of opening up, and the second one is opening down, and this shape is of course called a parabola. We also want to understand that quadratic functions have very specific critical values that are tested frequently on the SAT. So what are these critical values? First of all, it has a y-intercept, and again, that y-intercept is going to be a starting point. Now, for example, we might see a parabola model the trajectory of a ball or something like that being thrown through the air. So the y-intercept is where does this ball start in terms of its height at time 0. Then we of course have the x-intercept, okay? And that's the point of 0 value. Again, if we take that analogy of the ball, it's when does it hit the ground? When does it drop to a height of 0? Alternatively, if we're talking about profit and maximizing that profit, there will be a point where the profit level will come down to 0 and you'll be making no money. Again, that's the x-intercept. Finally, we come to the value of the vertex, and for the vertex, this is either going to be the maximum or minimum value, and it's usually denoted by h, k. Now, when we saw that first example where it opens up, there's going to be a bottom point, and this vertex will be that minimum value. And conversely, when it opens down, you see it looks like the top of a mountain, and then the vertex will be the max point. Now we want to talk about the format of quadratic functions when they're written out, and we're going to start with standard form. So standard form looks like this. It's y equals ax squared plus bx plus c. Again, a, b, and c are just constant coefficients. They can be positive or negative, and they don't have to be whole numbers. The highest degree, meaning the highest exponent, is 2. That's what defines a quadratic function. You can't have it to the 3rd power or the 4th power or anything like that. The highest degree has to be 2, and you can see there's that 2 right up there on connected with the a term. And by the way, the a term is always determined by whatever constant is multiplying the x squared. Now again, sticking with the fact that we recognize that there's our standard form at the bottom, I'm going to give you an example of one in standard form, and it's right here, 2x squared plus 4x minus 6. So this is a quadratic function with actual constant values in standard form. And notice, very interestingly, right, the 2 values, the a, the 4 values, the b, and the 6, but it's not just 6, it's actually a negative 6. We always want to be conscious of the fact that a minus sign is sticky, and it sticks to that number to the right, and it actually tags it as a negative number. And if we now look at the parabola and the graph of this, we can see that where does that negative 6 show up? It's very interesting because that negative 6 is actually the y-intercept. And it makes sense because if I zeroed out x, meaning if I plugged in 0 for x, I would get negative 6 for the function value. So there you see it on the graph, y-intercept of 0, negative 6. Now again, moving forward with this same function, we're going to put this exact function into what's called intercept form. Intercept form is also where it's simply factored. We're going to talk about factoring in a second. But what's interesting about intercept form is that the constants that are there show us what are the x-intercepts. And notice there's 2. Okay, there can be 1 and there can be none, but in this case there are 2, and it's that purple and that orange number, that 3 and that negative 1. But it's also important to note that when we see those values, it doesn't mean that there is an x-intercept at x equals 3 and x equals negative 1. In fact, it's flipped. So you'll see we have a x-intercept at negative 3, and that's really important too, because remember, the x-intercepts are where the function value is 0, meaning we're trying to find a value of x that zeroes out the whole function. So if I plug in a negative 3 into this binomial, it's going to be negative 3 plus 3, which is 0, and it's going to zero out the whole thing. Likewise, if I plug in a positive 1, right, you see that x-intercept of positive 1, 0, into here, it's gonna zero out this entire piece, which 0 times anything is 0. So again, we'll get a function value of 0. Now we're gonna talk about something called vertex form. So here's vertex form. It's y equals a times x minus h squared plus k. And in this case, that h and k value actually show us the vertex, remember, which is again either that max or min point of the function. So now we see that once it's reformatted in this form or presented in this form, that value, that purple value, is the h, which is the x coordinate of the vertex, and that yellow value, that -8, is the k value. This one is a little trickier because you have to remember to negate the purple one and keep the yellow one the same. So this is actually going to have a vertex of -1, -8. So you see that? So again, that one value is negated to its opposite, but that 8, which is a -8 actually, is kept the same as -8. Now let's talk about how do you find the vertex if it's not in vertex form. So again, if it's in vertex form, it's pretty easy to see, but let's take this example when it's in standard form. Now there's a really important formula that you gotta know in order to find the vertex. So when it's in standard form, you can find the vertex by putting -b over 2a, and then that will be the x value of the vertex. If we look in this example here, the 4 is the b value, so I say -4 over 2a. 2a is 2 times 2, so then we get -4 over 4, which of course equals -1, and that is the x value of the vertex. And again, as we saw before, there it is, -1, comma -8. Now how do we find that -8? You simply take the -1 value, that x value, and you plug it into the function. So just to show you what that would look like here, what we'd be doing is I'll take -1 and plug it in for all the x values. So first of all, it would be 2 times -1 squared plus 4 times -1 minus 6. This, of course, -1 squared is, of course, 1 times 2 is 2. 4 times -1 is -4, and -6 just stays as is. 2 minus 4 is -2, minus 6 is -8. So that gives us our corresponding y value of the vertex. Now let's talk about solving quadratic equations. So again, a quadratic equation is simply an equation where the highest degree is 2. So the first thing that we want to become aware of is factoring. So in order to factor this, we have to ask the question, what multiplies to -6, that green value, and adds to +5? Okay, so what would do that? Well, that would be 6 and -1, and that makes sense, right? 6 times -1 is -6, 6 plus -1 is +5, and that's how we split it up. We split it up into those two binomials, and if we were to FOIL, we would come back to that original equation. And now solving this equation gets really easy because I can look at each individual binomial and I say, hey, what makes the one on the left go to 0? Well, it's -6, because -6 plus 6 is 0. What about on the right? 1 minus 1 equals 0. So my two solutions are -6 and +1. Next, we're going to talk about something really, really powerful called the star method, and this has to do with factoring quadratic equations when there's a leading coefficient. So let's take an example here. We've got 8x squared plus 2x minus 3. So this is a lot more difficult to factor. So here's the protocol. And again, the chance that you're going to get something like this on the SAT is low compared to quadratics with a leading coefficient of 1. But I just want you to be aware of this and put this in your back pocket if you have the time to understand this technique. So check it out. What I'm going to do is I'm going to create this little star, and the top left and top right slots I throw in A. In the top slot I throw in A times C, and in the bottom slot is B. So let's check that out in practice. So I have 8 and 8 on the top left and top right. Again, that corresponds to the A value. Then I have 8 times -3 on top, which is -24, and I throw that 2 on the bottom. Now, why do I do this? Okay, because now I ask the question of what values of y1 and y2, meaning what two values can I find that multiply to -24 but add to +2. So the answer, of course, would be 6 and -4, right? 6 and -4 multiplies to -24. 6 plus -4 is +2. So we know that it's going to be 6 and -4, so I throw those down there. Now look at that 8 over the -4. Look at that 8 over the 6. Now I want to, those are the key pieces, right? Now I want to treat those like fractions. And so what I'm going to do is I'm going to reduce both of those, right? You notice that 8 over -4 reduces to 2 over -1. 8 over 6 reduces to 4 over 3. Now the most important part is we take that orange and purple value, that's going to make one binomial, and we take that blue and brown value, and that's going to make the second values of the second binomial. So this is how it looks. It's going to be 2x. Notice the top value always goes with the x. So it's going to be 2x minus 1 times 4x plus 3. And now we factored it. And what are the zeros in this case? Well, what makes that first binomial go to 0 is going to be 1/2. What makes the second one go to 0 is -3/4. So again, our answers for this are 1/2 and -3/4. Next, we're going to talk about another method, same thing for solving a quadratic equation, and that's called completing the square. Now, to me, completing the square is not really a necessary technique because you can always solve using either factoring or something we're going to talk about shortly, which is the quadratic formula. But the one good thing about the process of completing the square is it's helpful later on, which I'll show in another video, when you're trying to get a circle equation, for example, into standard form. So we're going to take this example of x squared minus 6x plus 8, and we're going to use the completing the square process to actually solve for x. So first what I'm going to do is I'm going to subtract both sides by -8. So you notice I put the -8 on the other side. Okay. Then the next step is that blue value, that's 6. I'm going to take half of that, which is 3, square it, and add it to both sides. So we take half the blue value, which is 3, and square it and add it to both sides. So I'm adding 3 squared to both sides. Remember, always must be a balance. We got whatever we do to the left side, we must do to the right side. So of course, 3 squared is simply 9. So I'm adding 9 to both sides. Okay, what I've done on the left side is created a perfect square, meaning it's perfectly factorable, and that's the whole point. What does that factor to? It's simply x minus 3 times x minus 3. And so when we sort of engineer the trinomial in this way, we're creating a perfect square. So now on the left side, I can factor that to x minus 3 squared. And of course, on the right side, -8 plus 9 just simplifies to 1. Now we're in a great position because I've got a square on the left side. How do I undo that? Simply take the square root of the left side and the right side as well. We have to keep the balance. So now it becomes, we get two equations. We get x minus 3 without the square equals +1 and -1, because the square root of 1 is plus or minus 1. All right. Now we have two great equations and we can solve both of those. So on the left side, we're simply going to add 3 to both sides and we get x equals 2. Beautiful. On the right side, same thing, add 3 to both sides and we get x equals 4. And if you want to double check your answer, take both of those solutions and plug them into the original equation. So the first one, it'd be 4 minus 12, which is -8, plus 8, 0. Boom, it works. With a positive value of 4, it'd be 16 minus 24, which is again -8 plus 8 is 0. Now let's talk about one of the best ways is just foolproof, it will always work, is the quadratic formula. So the quadratic formula, we're going to use this setup here and plug it in and show you how it works. Now to demonstrate the quadratic formula, we're going to start with this quadratic equation. So again, we're solving for x. And here's how it works. The quadratic formula is there's just something you got to memorize. You got to commit it to memory. -b plus or minus the square root of b squared minus 4ac over 2a. And now if you know that, it's just straight plug and chug, right? So guess what? The -4 is the b, the 2 is the a, and the -16 is the c. So you notice I just plugged all those in. I used blue to denote b, green to denote c, and red to denote a. Now we just multiply this out. And you notice, right, on top that 16, and then it ends up becoming plus 128, gives you that 144 under the square root. And the 2 times 2 at the bottom is 4. What's the square root of 144? It's simply 12. So now we got 4 plus or minus 12 over 4. So again, it's 4 plus 12 over 4, which is simply 4. And 4 minus 12 over 4, which again gives you -2. So those are the two solutions of this quadratic. Next, we're talking about exponential functions. This is also something that is tested on the SAT. And first, we're going to start with the standard form because you can learn a lot from the standard form. So standard form is y equals a times b to the x, where a is your initial value or starting value and b is the growth factor. So the initial value, if we want to think about a bacteria strain growing, we might say, okay, initially we have 500 cells, 500 bacteria. And b is the growth factor, meaning, hey, it's growing by maybe 5% every hour, something like that. Now in this example down here, we have 3 being the initial value, and here's a growth factor of 2, meaning it's doubling every time unit, whatever the time unit is, whatever x is. This is what the graph of this function would look like. So you notice that upward sort of curve shape. Now remember I said that the 3 corresponds with the initial value. Well, guess what? That also corresponds with that y-intercept. So you notice a trend. Initial values are the starting points, corresponds usually with that y-intercept value. Now there are 2 ways that exponential functions can go. They can either show growth or decay, where actually the value is declining or decreasing. So first let's talk about growth. So in the case of growth, we again have this standard form, and in this case b has to be greater than 1. It can be 1.1, it can be 1.001. That's still exponential growth. When we talk about percentages, this is what it looks like. Let's say somebody says, hey, it's growing by 5% every year. That means that the b is going to be 1.05. So what we do is we take that percentage, convert it to a decimal, or its decimal equivalent, and add it to 1. Okay, gotta add it to 1. Don't just put 0.05 in there. That would actually be decay. So now it's growing by 5% every year. So here now we have something with an initial value of 10 with a growth rate of 5% per year, week, month, whatever the unit is. And again, that graph looks like this, with our nice y-intercept again starting at the initial value of 0, 10. Now let's talk about decay. Decay is going the other way. It's starting high and going low. So in this case, with our standard form, the b value is going to be between 0 and 1. Okay, not negative, it's going to be between 0 and 1. So if we talk about percentages, and now we're saying it's decreasing by 5%. You don't put 5% in there. You put 0.95, okay? Why does that make sense? Because if I'm dropping by 5% every year, well, what am I retaining? I'm retaining 95%. So every year, I'm getting 95% of what I had the previous year. The other way to think about it is if it's 5% decay, you do 1 minus 0.05 and you get 0.95. So again, using that same example, a starting population of 10 decreasing by 5% every year, and that graph looks like this. Now notice it's got a negative slope, it's sloping down, but that initial value, same y-intercept of 0, 10. Now let's talk about radicals. We're taking roots, square roots, cube roots, all that stuff. So we're gonna talk about the most basic one, which is the square roots, okay? Square roots asks the question, what number times itself equals a given number? So for example, square root of 1, and let's just think about the positive roots for now. Of course, we can have negative roots, but square root of 1 is just 1. Square root of 4 is 2. Square root of 9 is 3, right? 3 times 3 equals 9. Square root of 16 is 4. Now notice I'm kind of skipping 10, 11, 12, 13, 14, 15 because they don't have nice perfect squares. They do have square roots, but they are irrational numbers. Square root of 25 is 5. Now if we look at variables, what's the square root of x squared? That's really simple, it's just x. We're sort of undoing that squaring operation. X to the 4th is x squared. Why does that make sense? Because remember, if I did x squared times x squared, we'd add the exponents and we'd get x to the 4th. Likewise, x to the 6th, I do x cubed times x cubed, we'd add the 2 3s, 3 plus 3, and we get 6. X to the 8th square root is x to the 4th, and finally x to the 10th, that square root is x to the 5th. Next, let's talk about cube roots. Cube root asks the question of what number times itself again equals a number. So again, the cube root of 1, that's still 1. That's nice and simple, right? 1 times 1 times 1 is 1. What about the cubic root of 8? Cubic root of 8 is 2 because 2 times 2 times 2 is 8. A few more examples. Cubic root of 27 is 3. And notice I'm picking perfect cubes again on the left side, 1, 8, and 27. Next would be 64. Cubic root of 64 is 4. And last but not least, cubic root of 125 is 5. Now we're going to talk about with variables. Again, cubic root of x cubed has to be x. That makes sense. But now we have something like x to the 6th. It's x squared. So you'll notice a trend. It's almost like I'm dividing that exponent by the root, right? 6 divided by 3 is 2. 9 divided by 3 is 3. And if you're not sure if this is right, again, always double check. What's x cubed times x cubed times x cubed? We add all three of those exponents, we get x to the 9th. X to the 12th would be x to the 4th. And last but not least, x to the 15th would be x to the 5th. Now let's talk about simplifying radicals, okay, and simplifying these roots. So here's a perfect example. We're gonna start with the square root. Now you notice there's no number. When there's no number, you assume it's a 2, so it's just a square root. So how do we take the square root? This is my way of doing it, and I think it's really helpful. I like to break everything up into perfect squares. So for example, I'm taking from that 32, I'm representing that 32 as 2 times 16 because 16 is a perfect square. I'm taking that x cubed and I'm representing it as x times x squared because at least I've got one perfect square in there, x squared. Y6 is already a perfect square because it's a nice even exponent. And then I'm taking that z and I'm breaking it up into z times z to the 8th because z to the 8th is a perfect square, okay? Why do I do this? Because I think of a square root as a prism. The only thing that can come out is perfect squares, and it comes out as the square root. So for example, I can now take the square root of 16, which is 4, beautiful. I can take the square root of x squared, which is x. I can take the square root of y to the 6th, which is y to the 3rd. And I can take the square root of z to the 8th, which is z to the 4th. Everything else is stuck inside that square root prism, so the 2xz stays inside, and then we have it's fully simplified. Now let's talk about solving equations involving radicals. So we start off with something like this. The square root of x plus 1 equals x minus 5, okay? Job number 1 is to get rid of that square root. How do we do that? We do the inverse operation, which is squaring both sides, right? So you notice we got to square the left side and the right side. But that right side is a binomial, so don't make it x squared plus 25, okay? It's a big mistake. Instead, it's x minus 5 times x minus 5, so you got a FOIL, right? And we get x squared minus 10x plus 25. And if you're not sure how I did that, remember, it's gonna be x minus 5 times x minus 5, and you've got to do that foiling process, and then you'll see you get x squared minus 10x plus 25. Next, I'm going to subtract x and subtract 1 from both sides because I want to get 0 in this. Anytime we're dealing with a quadratic, again, degree of 2, we want to get everything equal to 0. So negative 10x minus x is negative 11x, and 25 minus 1 is 24. So we got x squared minus 11x plus 24. Now, if possible, I'd love to factor. If that doesn't work, of course, we got the quadratic formula, but this is factorable. Again, we're asking the question, what multiplies to 24 and what adds to negative 11? That's negative 3 and negative 8. So what are the zeros, or what are the solutions? What makes each binomial go to 0? It would be positive 3 and positive 8. But there's a final step with these radical equations. You've got to check both zeros to make sure they are legitimate solutions. They're not extraneous solutions. So how do we do that? All right, we're gonna plug them into our original equation, and notice here now, we're only talking about the positive roots, not the negative roots. Remember we said before, square root of 4 is both 2 and negative 2. We're only taking the positive one here. So first let's check that 3 value. So you notice I'm plugging 3 in for x. So 3 plus 1 on the left side gives us the square root of 4. On the right side we get negative 2. Square root of 4 is positive 2. Again, we're only taking the positive root in this case. 2 does not equal negative 2, therefore 3 is extraneous. Now chances are if one's extraneous, the other one's probably going to be legitimate, but we have to check anyway. So now I'm plugging in the 8. I get 8 plus 1 on the left side, 8 minus 5 on the right. That becomes the square root of 9 equals 3, and guess what? Square root of 9 is positive 3 in this case. That solution is valid. Something else we might come across with radicals is rationalizing denominators. What does this mean? It means that if I take a radical like 3 over square root of 5, we have a rule in mathematics that we don't want to have a radical in the denominator. It's just something you have to become familiar with. It's a formatting thing, almost syntax. So we see a square root of 5 in the denominator, chances are that the answer choice is not going to have a radical in the denominator, so we must rationalize the denominator. Believe it or not, this is actually pretty simple, because I can obliterate that square root 5 simply by multiplying it by square root of 5. But again, I can't just multiply the denominator, right? I have to also multiply the numerator by the same value, otherwise I'm changing the value of the fraction. So I multiply top and bottom by square root of 5. The nice part about square root of 5 times square root of 5 on the denominator is it simply 5. And on the top, we get 3 radical 5. So now we've rationalized the denominator. This is the proper format. So a lot of times when they say to simplify an expression with a radical, all they're asking you to do is get rid of that radical in the denominator. Let's take a more complex example where we have 3 over 4 plus square root of 5. Now it's not so easy, because if I just multiply it by root 5 over root 5, the problem on the bottom is that root 5 is going to distribute, and I'm going to get 4 root 5 plus 5. It's no good because I still got a radical. Now we have to be a little smarter, and we have to use something called the conjugate. So it's the same thing as 4 plus radical 5, except we just flip the plus to a negative. If it was a minus, we'd flip it to a positive, so we just make it opposite. Okay, again, now we FOIL that denominator. But you don't even really have to FOIL, because it works out perfectly so that the middle terms cancel out, because what you get is 16 minus 4 radical 5 plus 4 radical 5 minus 5. But the middle terms cancel out because they're opposite, so all we get is 16 minus 5 on the bottom. So super nice, right? And again, radical 5 times radical 5 just turns into a 5, but there's a minus there, so it's negative. And on the top, we just distributed the 3. 3 times 4 is 12. 3 times negative rad 5 is negative 3 rad 5. On the bottom now, we simplify. 16 minus 5 is simply 11. Now we've got our nice fraction with a rational denominator. Just as a little explanation of how this times this gives me this, let me just show you how it would FOIL. We'd have 4 plus square root 5 times 4 minus square root 5. This would FOIL like that and like that. So what do we get? We get 16 minus 4 rad 5 plus 4 rad 5. Rad 5 times negative rad 5 is just negative 5. The square roots go away. These guys are opposite. They cancel. And hence we're left with 16 minus 5. Now we're going to talk about rational exponents, a little bit of exponent rules. So check it out. If I have a to the 2/3 power, what does that mean? Well, we look at the numerator always as the power and the denominator as the root. So how can I rewrite this as a radical? Okay, it's super nice. I can say that it's 8 squared and the cube root of that. I can also write it in the opposite way, where I can take the cube root of 8 first and then square it afterwards, which means that the order in which I apply these exponents, whether it's a root or a power, it doesn't matter. We're gonna get the same answer, and I'm gonna show you now why. So first, we do that 8 squared, which gives us 64. What's the cube root of 64? Meaning what number times itself and then times itself again is 64? That's 4. What about if we go to the right side first? What's the cubic root of 8? It's 2, because 2 times 2 times 2 is 8. And then what's 2 squared? It's also 4. So notice, you get the same thing both ways. And I usually prefer the method on the right, because I like to go small then big, not really big and then have to come back and go small. It's usually easier. Another quick rule that we want to be aware of is when we multiply and divide involving exponents. So really quickly, I'm going to give you 2 short examples that are tested quite frequently. So remember, let's say I've got the same base, has to be the same base. So we got the same base of x, and I've got x to the 7th times x to the 4th. What does that equal? That equals the sum of those exponents. So when we multiply, we're really adding the exponents. So it becomes 7 plus 4, which is x to the 11th. What about when we divide? So let's say now we got the same thing, x to the 7th divided by x to the 4th. Again, it has to have the same base. And now instead of adding, we subtract the exponents. So it's 7 minus 4, which equals x to the 3rd power. Next, we're going to talk about simplifying rational expressions. So I'm going to give you an example of a rational expression, which is basically a fraction of expressions. So we got this one here, but then let's make it more complicated. We're dividing by this other crazy rational expression. All right, so there are a couple of steps that you just got to follow no matter what. First of all, when we're dividing, we don't want to do that. We want to immediately shift that to multiplication. So we employ keep, change, flip. I keep the first rational expression. I change that to multiplication, and I flip the other one to 3x over 9 minus 15x. Then we go into a rule that I advise to everybody, that when you see a quadratic like this and you're not sure what to do, simply factor. So now I'm going to start factoring everything. So we're going to factor all these expressions. So on the left, the 3x squared minus 2x minus 5 factors to 3x minus 5 times x plus 1. On the bottom, we factor out an x, and it's just simply x times x plus 1. On the right, the top we can't do anything, but the bottom we can factor out a 3, and it's 3 times 3x minus 5. Now it's almost like one giant fraction because it's all multiplying. So the numerators and the denominators kind of combine, which gives us a great opportunity to cross cancel. So I see I've got those 3x minus 5s that I can just knock out. I've also got x plus 1s on the top and bottom that I can knock out. I've got a x on the top and bottom that also can get knocked out, and also those 3s knock out. What happens when everything knocks out? When everything knocks out, you don't have 0, by the way, you have a 1. Okay, so everything on top is equal to everything on bottom. It's just like 5 divided by 5 or 10 divided by 10. It's 1. Now we're gonna talk about polynomials. What's a polynomial? This is a polynomial, x cubed plus 2x. 4x squared plus 7x minus 3. That's a polynomial. Poly meaning multiple terms, okay? This is a polynomial. This has 5 terms, right? And in a degree of 5 because the highest exponent is 5. Okay, what is a monomial? Not so much that you need to know these names per se, but a monomial is, again, not many, but simply one term like 3x to the 6th. Now let's talk about operations with polynomials. So again, adding and subtracting is pretty straightforward. So let's take this example. We've got 3x squared minus 2x minus 5 plus 4x squared plus x plus 2. The first thing you see is that they are in parentheses, but are the parentheses doing anything? No, there's nothing out there multiplying. There's no minus sign, so I'm just going to get rid of those parentheses. And now I combine like terms. So you notice we have the x squareds, right? Those are like terms. We have the just simple x's, and again, that's a negative 2x, don't forget that minus. And then we got the 5 and the 2, but again, a negative 5 and 2. Now we combine, so the 3x squared and the 4x squared becomes 7x squared. Negative 2x and positive 1x becomes negative x. And negative 5 and positive 2 combine to become negative 3, and that's that. Well, what about if we had a subtraction going on here? Okay, so now we can't just get rid of the parentheses so easily. We have to remember that on the right side, that's really like a negative 1. So we have to distribute that minus across those 3 terms on the right. So now we have same thing on the left, but we have minus 4x squared minus x minus 2. Again, let's identify the like terms with the x squareds, the x's, and the constants. 3x squared minus 4x squared is negative x squared. And I put the 1 there, you don't have to, but it is negative 1x squared. The negative 2x and negative x, both same team, both negatives. So we got negative 3x, and last but not least, negative 5 and negative 2 make negative 7. Now let's talk about multiplying polynomials. So we've got 2x minus 5 times 4x squared plus x plus 2. Again, we're sort of doing the foiling operation. So if you guys had questions about that, this is how it works. Very straightforward. Essentially, everything in the first one has to multiply at some point everything in the second one. And this is a nice order to go in. So first I do 2x times 4x squared, which gives me a nice 8x cubed. Again, the exponents are being added, and that x is also x to the first. 2x times x gives me 2x squared. And then 2x times 2 gives me a nice 4x. Now we start with the negative 5, and we say negative 5 times everything. Negative 5 times 4x squared is negative 20x squared. Negative 5 times x is negative 5x. And last but not least, negative 5 times 2 is negative 10. Now if we have any like terms, we should combine, and I see 2x squareds and 2x's. So 2x squared plus negative 20x squared is going to give me negative 18x squared, and 4x plus that negative 5x gives me a negative x. The 8x cubed and the negative 10 stay as they are. Next, let's talk about synthetic division, which does come up, not super often, but it does come up, and this is where we're dividing polynomials. I've got this polynomial here, x cubed plus 4x squared minus 3x plus 1 divided by x minus 1. So here's a little refresh on synthetic division. What you do is we drop all the coefficients from that original polynomial. Okay, I got a 1, I got a 4, I got a negative 3, and I got a positive 1. Boom. Then I take the opposite of what's in that other binomial that it's dividing by. And this only works, by the way, if we're dividing by a binomial and we've got no coefficient in front of the x. So I'm taking not a negative 1, but a positive 1. Now here's the process. Throw a line down here. First thing is we just drop the blue 1. Then we take that and we multiply it against the 1 in the box, and then take that product and throw it down here. And again, we add. 4 plus 1 is 5. Repeat. 5 times 1 is 5, and we throw the 5 over here. 5 plus negative 3 is 2. Again, repeat, 2 times 1 is 2. Throw that over here. 1 plus 2 is 3, and we're done. But what is this? These are just numbers. Okay, this is how it links back. That 1 is the coefficient of, notice, an x squared, not x cubed, because we divided, right? So the result is going to be a degree lower. The 5 goes with the next one, x, 5x. The 2 goes as a constant, and then we actually have a remainder. Now, if you end with a 0, it means there's no remainder and you're done. But since we do have a remainder, we have to throw it on top of that original divisor, which is x minus 1. And there you go. By the way, the fact that we have a remainder means that 1 is not a factor of this original polynomial, of the polynomial on the left, meaning if I plug 1 in, I won't get 0. In fact, the remainder theorem states that if I plug 1 into that polynomial on the left, I will get that remainder of 3. Now I'm going to show you how we do long division, because long division comes into play when we do have a coefficient in front of that x value. So let me show you how this works. We take the original polynomial, then divide it by that binomial, and we have an actual long division symbol. Now, the first thing that I ask is I only look at that leading term, the 2x, and the biggest one, starting with the biggest one of the inside polynomial, which is 4x cubed. And I say, what times 2x gives me 4x cubed? Okay, that would be 2x squared. Then I multiply the 2x squared times that entire binomial. So I get 4x cubed, right, add the exponents, minus 2x squared, because 2x squared times negative 1 is negative 2x squared. And now I subtract the bottom number, so I do it like this. I negate and negate, right? I'm distributing a negative. And the negative 4x cubed and the 4x cubed cancels out. That's what I wanted. 4x squared plus 2x squared gives me 6x squared. Now, just like in long division, I drop the next term of negative 8x. And now again, I ask the question, what times 2x gives me 6x squared? That would be 3x, positive. 3x times 2x is 6x squared times that negative 1 is negative 3x. Again, I negate because I'm subtracting. 6x squared minus 6x squared gives me nothing, which is what I wanted. And then negative 8x plus 3x is negative 5x. Again, I drop the 1 and we repeat it one more time. So what times 2x gives me negative 5x? That would be negative 5 over 2. Negative 5 over 2 times 2x gives me negative 5x. And then negative 5 over 2 times negative 1 gives me positive 5 over 2. Negate, negate. And again, negative 5x plus 5x is nothing. And the 1 plus negative 5 over 2 is negative 3 over 2. So again, I have a remainder of negative 3 over 2. And the final polynomial looks like what I got on the top, 2x squared plus 3x minus 5 halves. And then minus 3 over 2 over that original divisor. But again, it's a fraction. You're dividing so that it becomes 3 over 2 times 2x minus 1. Now we're going to talk about factors of polynomials. So just some simple examples. We got x squared plus 2x. Here we can factor out an x, and we've got two factors. We've got x and we've got x plus 2. Then in this one, we again follow that same protocol, what multiplies to 10 and adds to 7. That's positive 2 and positive 5. And with a more complicated one, this one factors out to 4x minus 1 times x minus 2 times x minus 3. So what do these factors mean in terms of zeros? So let's go through the list again. So we've got this one that factors to, and now look, I'm expressing it as a function. I've got a function of x times x plus 2. It means that I have two zeros at 0, because when I plug 0 in for x on the left, it zeroes everything out. If I plug in negative 2 into that binomial, x plus 2, I get a 0. When this guy is factored, again, I have zeros at negative 2 and negative 5. And last but not least, with the big dog, if I factor that one, I've got 3 zeros, right? Because the fact goes into 3 factors. Positive 1/4, positive 2, and positive 3. Now let's talk about the graphs of these polynomials, especially that more complex one that we saw at the end, 4x cubed minus 21x squared plus 29x minus 6. So when we factor it and we know that the zeros occur at 1/4, 2, and 3, what does that look like on the graph? Again, the zeros are the x-intercept. So if I look at this function, you notice that I've got a 0, aka an x-intercept, at 1/4 0, at 2 0, and at 3 0. Next, let's talk about linear and quadratic systems, okay? These are systems of equations. Anytime you're thinking about systems, you're thinking about points of intersection. So for example, if we've got y equals x squared minus 6x plus 3, and then which is the quadratic, and then we got a linear of negative 2x plus 3. If we look at those two on a graph, one's a line, one's a parabola, and we're looking for the intersection points. Those are the solutions. So the two solutions are 0, 3, and 4, negative 5. Now, if I didn't have a graph like this to show me the intersection points, there's another way that I can solve this just by simple substitution and isolation. So I can plug in negative 2x plus 3 for the y up top. So let me show you how that looks. So I have negative 2x plus 3 equals x squared minus 6x plus 3. Now I want to isolate, so I'm going to add 2x to both sides, because again, we always want to set everything equal to 0. And I want to subtract 3 from both sides, okay? That cancels, that cancels. Now I have 0, which is exactly what I want, equals x squared minus 6x, negative 6x plus 2x is negative 4x. These guys cancel out. Again, now we're going to factor. So again, here's just a simple factoring. I can factor out an x, and I get x minus 4. So again, if I distributed that, I get x squared minus 4x, which is what we want. And what are my two 0 values? What zeros this out? It would be 0 and 4. And if you notice on the graph, there's the 0 and there's the 4. Now, if I wanted to get the corresponding y values, I just plug in those x values into either of these equations, and I'll get the right y value. Next, we have structure in expressions, another subcategory. What we're doing here is we're basically just combining these two rational expressions. And the way we want to think about it is the same sense that we think about combining fractions, getting common denominators. So let me show you how this works. So the thing is, I look at this and it almost looks like they have the same denominator, except for this is flipped. So I can real easily factor out a negative 1 out of this expression and flip it to c minus d, okay? By the way, if I factor out a negative 1, it's going to come up top and make this whole expression negative, but it's going to nicely cancel out with that negative in here, that minus in here. So watch what's going to happen. It's going to be a plus b over c minus d, that's fine, plus, because again, I factored out a negative, which flips this into c minus d, and then it cancels out with that minus. And then I got a plus b on top. Now what's going to happen? Now I've got common denominators, very straightforward, just add the numerators. So if I add a and a, I get 2a. Add b and b, I get 2b over c minus d. And that's it. That's our fully simplified expression. And next, here's another example of a problem where we see on the left, it's x cubed plus b cubed equals this whole craziness on the right side, right? A binomial times a trinomial. So how do you approach something like this? Well, you start by recognizing that the two sides are equivalent. And again, my advice is always, if you see something in its normal form and it's a quadratic or higher, factor it if you don't know what to do. Here, it's already factored. Well, what should you do? The opposite of that, which is foiling. So let me show you. So first I'm going to start by distributing, boom, boom, and boom. So I got x cubed minus x squared b plus 9x. Now I'm going to start with this guy. Now notice how I'm going to just kind of lay it out a little bit differently, and you'll see why in a second. So I'm going to do b times x squared, or let's call it x squared b. And then I got negative b squared x. And then last but not least, I got 9 times b. Okay, the reason why I did it like this, first of all, these cancel out, which is great. These kind of combine because they're both x terms, or they can be grouped together. And then I got 9b at the end. So I've got now on the right side, x cubed plus 9x minus b squared, x plus 9b. So there's two things that are important to note if I'm trying to figure out what the value of b is. Number one, there's no x term on this side, which means that these guys are probably going to zero out. The second thing is that 9b equals b cubed. I can use either of these to solve for b. Let's use the 9b equals b cubed. So, because 9b is the constant here and b cubed there. So if b cubed equals 9b, I can divide both sides by b, and I get 9 equals b squared, which means that b is going to give me a value of 3. Next, we come to one of my favorite categories, which is isolating quantities. And why do I love this so much is because usually isolating quantities questions have all this dense verbiage and they go through this in these complex passages, but they're really meaningless because you look at the answer choices and you're like, oh, they're just isolating one variable in this equation. So I'm gonna give you this example of a equals 1 plus r to the t power, and we are trying to isolate r. That's why I put it in red. So let's go through the process. So all we're gonna do is we're gonna first get rid of this t. Well, first of all, how do I do that? It's to the t power. So what's the opposite of taking something to the t power? Taking the t root. So for example, I'm gonna take the t root of a and the t root of 1 plus r to the t power. These cancel out. Now I have the t root of a equals 1 plus r. Last but not least, I need to get rid of that 1, so I'm going to subtract 1 from both sides, so we could say the t root of a minus 1 equals r, and we have successfully isolated r. Finally, we come to function notation. So function notation is just simply knowing function notation, understanding how to apply it. So I'm going to give you a couple examples of a function. So for example, we have f of x equals 3x plus 7, g of x equals 5x, and h of x equals x squared plus 3. What the heck are these f of x, g of x, and h of x things? It just means function f, function g, and function h. And the reason why I have the parentheses and the x, it doesn't mean it's f times x. It means it's function f, which has a variable of x. You can literally substitute y in. The function value is the same as the y value. That's it. Now we're gonna go through some other examples where what if they ask, hey, there's f of x, we wanna know what's f of 3, we wanna know what's g of 0, and we wanna know what's h of negative 2. This is where understanding the notation comes into play. So if I want f of 3, they literally mean to replace the x with 3 in this function. So it becomes 3 times 3 plus 7, which is simply 9 plus 7, or 16. Same with this one. I want to plug 0 in for x here. So it's simply 5 times 0, which is 0. Last but not least, I want to plug in negative 2 into my x for h. So it becomes negative 2 squared, don't forget the whole thing is squared, plus 3. That's 4 plus 3, which equals 7. Another example involving all three of these original functions, it would be f of 1 plus g of 3, addition, g times h of negative 1. What the heck is that? We're going to talk about that in a second. And then this interesting open circle. So let's go through all these examples. The first one is pretty straightforward. We're simply plugging in 1 for f of x and 3 for g and adding them together. So it'd be 3 times 1 plus 7, that's my f of x, plus g of 3, which is 5 times 3. This becomes 3 plus 7 is 10, plus 15 gives me a nice 25. In this example, they're saying g times h of negative 1. Okay, so there's two ways we can think about this. This is basically saying negative 1 is going in for g and h, and we are simply taking negative 1 of each and then multiplying those two values together. And that's the way that I like to do it. So let's just roll with that. So first, what is g of negative 1? That's negative 5, right? Because I'm plugging in negative 1 in for x times 5 is negative 1. What is h of negative 1? That becomes negative 1 squared plus 3. Again, negative 1 squared is just 1. So 1 plus 3 is simply 4. And then what's 4 times negative 5? Negative 20. Last but not least, what is this? This, when you see an open circle, is not multiplication. It's a little different. This is saying h, I like to rewrite it like this, h of g of negative 2. Now what are we doing here? We're plugging negative 2 in for g and we're evaluating that first, and then whatever value we get there, we plug that into h. So what is g of negative 2? It's negative 2 times 5, which is negative 10. So I always go inside out. That's why I say. Now we're taking h of negative 10, so I plug that in up here. And I've got, here, let's write it over here, negative 10 squared plus 3. Negative 10 squared is 100 plus 3, and we get 103. That's it for part 2 in this 4-part series. I hope you guys enjoyed all these math concepts, and I hope it helps you on your SAT math journey. Thank you so much for joining, and I will see you in the next video. Take it easy.